Let's revisit this problem and see how using the method of flowchart can help to better organize the logic of dividing the problem into separate cases and examining each case. First, let me repeat the description of this problem. We must consider all the right triangles, like the one shown on the diagram, whose three vertices can be any points of intersection of grid lines shown on this diagram, except the origin of coordinates 0, 0. For each such triangle, we must calculate the ratio of side lengths AC to AB, assuming that letter A denotes the vertex at the right angle and vertex B is positioned counterclockwise from vertex A. This ratio is called tangent of angle B. We must multiply all the ratios, and their product is the answer to the question of the problem. This is a flowchart of testing any triangle from set T which contains all the triangles that don't have any vertices at the origin, to check if this triangle must be counted individually in the product of tangents of angle B. The first test checks if the sides AB and AC of the triangle are parallel to axes X and Y. If sides AB and AC are parallel to X and Y axis, we need to further check if vertex A of this triangle is symmetric to the origin point 0, 0 with respect to the midpoint of the hypotenuse BC. If it's false, that is, vertex D opposite to vertex A of the rectangle ABDC is not at the origin, then this triangle belongs to the pair of triangles from set T whose tangent B values are reciprocal to each other and cancel each other in multiplication. But if it's true, meaning that vertex D of the rectangle is at the origin, then the other triangle from this pair has its vertex in the origin point 0, 0, so that this triangle does not belong to set T, but the first triangle does. Therefore, its function f, that is equal to tangent of angle B, must be counted in the final product. Now let us look at each such triangle, calculate tangent of angle B in it, and then multiply these numbers. Once we have discovered our method, at this point it's a no-brainer. We will just skip the isosceles triangles, since tangent of angle B for such triangles is equal to 1. So let's calculate tangent of angle B for each such triangle. 5 to 1, 5 to 2, 5 to 3, and 5 to 4. 4 to 1, 4 to 2, 4 to 3. 3 to 1, 3 to 2, 3 to 4. Then 2 to 1, 2 to 3, 2 to 4. And finally 1 to 2, 1 to 3, and 1 to 4. Let's calculate their product. It's equal to 625 over 24. Notice that we only need to multiply the fractions in the first row, since the last 4 rows consist of pairs of fractions that cancel each other in multiplication. These pairs of reciprocal fractions can be easily found. As an exercise, find the geometric justification of this fact. We're done with the case of right triangles ABC, whose A and B sides are parallel to axes X and Y. Let's now get to the case of right triangles whose sides AB and AC are not parallel to X and Y axes. The first test for this type of triangle is if the triangle symmetric to it with respect to the central vertical line has origin point 0, 0. If it's false, that is, the symmetric triangle does not have any vertex at the origin, then these two triangles have the values of tangent B reciprocal to each other and cancel each other in the multiplication. If the symmetrical triangle is the same as the first triangle, then this triangle is isosceles, and the value of its tangent B is equal to 1. If the first check is true, that is, the triangle symmetric to this triangle over the central vertical line has a vertex at the origin point 0, 0. Then the next check is if the entire triangle lies within the square with side length 4 and bottom left corner at the origin 0, 0. If it's true, then this triangle has a unique other triangle that is symmetric to it with respect to the diagonal line marked on the diagram with blue color. The values of function f of these two triangles are reciprocal to each other. If the second check is false, it leaves the last three cases. The highlighted triangle on the diagram is a right triangle, since angle A is the sum of two 45 degrees angles. The value of function f, that is tangent of its angle B, is equal to 1/4, and its counterpart symmetrical to it over the central vertical line. The second triangle that is not highlighted has its vertex in the origin of coordinates, so it is excluded from set T. Since the highlighted triangle ABC is included in set T, its value of function f, that is equal to 1/4, must be counted in the final product. The same is true for two remaining cases, this one and this one, even though tangent B for the last triangle is equal to 1, so that this triangle doesn't really matter. Thus, we must multiply the values of tangent B for this category of triangles, which includes only two triangles. The result of this multiplication is 1 divided by 6. The conclusion: we must now multiply two products of function values we calculated earlier for the two cases of triangles. The final product is equal to 625 over 144. The answer is B.